Hello everyone and welcome back to the channel. In this video we're going to talk about basic set theory and classical probability. This is the last topic for our curriculum for grade 6. Without further ado, let's jump into the lesson. So the first thing we want to know is what is a set. So let's give a definition. A set is a group of objects or elements with a common characteristic or characteristics. All right, so when you think of a set at this level, we are going to think of some grouping of objects. For example, in everyday life, I can look around and I can see all kinds of sets, right? All kinds of objects with common characteristics. For example, I have the set of the objects on my desk right now. I have a coffee cup, I have my phone, I have my mouse, my papers, my computer, and so on and so forth. All right. When you go to school, your classmates in your class represent a set of students. The set is the class that you go to. You can think of the students in the entire school as a bigger set, right? Which contains the smaller set, the students of a particular class in grade 6. So a set is just a grouping of objects or elements with some characteristic. Doesn't matter what the characteristic is. Okay, if I have a backpack, the objects in my backpack can be considered as a set. The characteristics is that they belong to the same backpack. Okay, they are in the backpack. That's the characteristic which unites them. Okay, so yeah, that's a set. Now sets and B, let's write sets can be finite or open-ended. For example, the set, let's say from A to Z, A, B, C, etc., to Z, all the small letters in the English alphabet. This is a finite set. It has only 26 elements, right? But the set, for example, that we denote with N, the natural numbers 1, 2, 3, and so on and so forth, is open-ended. I can add more and more elements because I cannot put a limit to all the natural numbers, right? So this is the difference between finite and open-ended sets. One has a fixed number of elements, like 26 or whatever it's the number, and the other is just it has countless elements. All right. Now number 2, notation. The first thing about notation, I've already indicated it here. When I want to specify the concrete elements in a given set, I use these curly brackets here, okay? These curly brackets. So I use curly brackets to enumerate or list the elements of a set. So for example, the set of 1-digit numbers, all right, the set of distinct digits will be like A equals, and now I just list the elements, so 0, 1, 2, 3, etc., to 9. and this set has 10 elements. I have 10 different digits, okay? And I use the curly brackets to indicate that I'm enumerating specific elements, that I'm indicating which elements are in that set. Now B, if I want to indicate that a specific element belongs to a set, I use a special symbol. X belongs to the set A. We read X belongs to A. Okay, this symbol indicates belonging. It's a very important symbol because we're going to use it in inequalities. We're going to use it in all kinds of contexts, when finding domains of expressions and so on and so forth. So this symbol will come up a lot later, and it's very important to remember it. This means that some element belongs to some set, okay? Obviously, it should be clear that sets are denoted with capital letters. Now, C, this symbol here is called the empty set. The empty set, that is the set with no elements. The set with no elements. So for example, if my backpack is empty, right, the set of objects in my backpack will be the empty set. If my equation has no solution, if I'm solving an equation and the equation has no solution, this means that the solutions represent an empty set, right? There are no numbers that represent roots of my equation. Then another very important thing is a Greek letter. This is the Greek letter. We read it as ni, okay? The Greek letter ni, all right, indicating the number of elements in a set. So let's give this example. A is okay. I'm listing the elements like before. Let's say A is the set of all small letters in the English alphabet. So A, B, C, etc. to etc. to Z. So I write like this: ni of A equals 26, right? How many elements are in the set? This is what ni indicates. There are 26 elements in this set, so ni of A will be 26. Then if I have the digits 0, 1, 2, 9, ni of A will be 10, the number of elements, 10 elements, all right, and so on and so forth. Okay, so far so good. Number 3, a subset. If all elements of the set B are contained in the set A, then B is called a subset of A, all right? For example, let's give this example. So A is the set of digits from 0 to 9. Good. Curly bracket. And B is just the set of odd digits from 0 to 9. So it will be 1, 3, 5, 7, and 9. Obviously, all the numbers that are in B are already contained in a bigger set, the set A. So we write B is a subset of A. This symbol here indicates subset. It's similar to the symbol of belongs without the middle line, okay? And another thing we can say is that every set is a subset of itself, okay? Because obviously every set contains the same elements that are in the set itself. Two sets are equal, another thing, two sets are equal if they contain the same elements. Okay. So far so good. Let's go to union and intersection. The union of two sets A and B is a set that contains the elements which are either in A or B. Okay, so union is equivalent to the logical operation OR. For example, if I have A contains 1, 2, 3, and 4, let's say, and B has 3, 4, 5, 6, like the numbers, then A union B will contain 1, 2, 3, 4, 5, and 6. So all the elements, right? All from A or B, we combine them together. And probably you know about Venn diagrams. We represent sets with circles. So let's draw a Venn diagram to illustrate the union real quick. So this is A and this is B. Okay. So A has 1, 2, 3, 4, 1, 2, 3, 4, and B has 3, 4, 5, and 6. So the union will include everything. This is the union, okay? A union B. Let's go to intersection. The intersection of two sets A and B, we denote it like this. This is the intersection with this U in reverse. Is a set that contains only the elements that are both in A and B. Okay, so the intersection is equivalent to the logical operation AND. Okay, so A and B. In our previous example, A was 1, 2, 3, 4. B was 3, 4, 5, and 6. So A intersection with B will contain only 3 and 4, the elements that are in A and in B. Okay, let's draw real quickly a Venn diagram. A and B. So 1, 2, 3, 4, 5, and 6. So only this part will be the intersection, A intersection with B. Okay, does it make sense? Hopefully this makes sense for you. And we can see that if B is a subset of A, it follows that A union B will be the same as A, and A intersection B will be the same as B. For example, if A is 1, 2, 3, 4, B is 1, 2. Okay, so what is the union? A union B, all the elements that are in A or in B, but all the elements are in B are already in A, so the union will be just 1, 2, 3, 4. That is the same as A. And the intersection, the elements that are both in A and in B will be just 1 and 2, right? Those are the elements that are both in A and in B, and that's equivalent to that's equal to B, right? So far so good. Let's go to the next thing. So this was 4, so number 5, events. Wow, now we're going to talk about events first. And now this is important from consistency, and what we call an elementary event. What is an elementary event? Now this is a nice topic. This is the concrete, observable outcome of a given experiment. Okay, and we are going to contrast this with complex events. We are going to talk about complex events in just a minute. But what is an elementary event? So if I roll a 6-sided die and I get the number 6, for example, now this is an elementary event. I observe the 6 on the die when it stops rolling. Okay, if I draw a card out of a deck of cards, I get let's say the 2 of hearts. This is an elementary event. I observe that I'm holding the 2 of hearts. Okay, if I spin a ball on a roulette, let's say, and I get the number 10, that's an elementary event. I can observe directly that I got 10, and so on and so forth. Okay, the concrete, the observable outcome of my experiment, of what I'm doing. B, a complex event. Okay, an event which has more than one outcome how to say, which involves more than one outcome will be more correct expression, which involves Okay, so what event would involve more than one outcome? For example, I roll a 6-sided die, and how many outcomes are for the event occurring? I get an even number, let's say. Now when I look at what I got on the die itself, it's not written even number. It doesn't say on the face of the die even number. It can say 2, it can say 4, or it can say 6, right? So these three outcomes, getting a 2, getting a 4, or getting a 6, will be outcomes that satisfy the event getting an even number. And therefore, when I formulate it like this, my event, what I want to happen is I want an even number. That's a complex event that involves 3 elementary events or elementary outcomes, getting a 2, a 6, or a 4. With the example of the deck of cards, let's say I want to draw a card out of the deck and I want a diamond. Doesn't matter what diamond, just a diamond. Now this is a complex event because I can draw the 2 of diamonds, I can draw the ace, the 3, the 4, the jack, king or queen, etc, etc. So I have more than one outcomes that satisfy my required event to draw a diamond. And in this case I'll have 13 different elementary events as possible outcomes that satisfy drawing a diamond, because there are 13 diamonds in the deck of cards. Okay, another thing, like if I spin the roulette, I can have my bet can be on red or black, and I don't really know honestly how many numbers in total are on the roulette. I think there were like 36 or 34, something like that. So half of them will be red, half of them will be black. So I have like 16 or 17 possible outcomes if I want a red number or a black number. Okay, if that's clear, let's go to the next one. And now this is a very common sense thing. A certain event an event which will happen for sure. Example, I roll a die and I want a number that is less than 10. Now obviously all I can get from rolling the die are numbers from 1 to 6, and obviously all these numbers are less than 10, so it doesn't matter what I roll, it's going to be always less than 10. All right, so this is a certain event. Then A, B, C, D, an impossible event. An event which won't happen for sure. Okay, so let's for example, when I roll the die, that's an the easiest kinds of examples to give. When I roll the die and I want to get a number that is greater than 10, okay, that's not going to happen. I'll get numbers from 1 to 6. None of them are greater than 10. All right, and finally, a casual event. An event which may or may not happen. For example, I roll the die and I want to get a number less than 4. Maybe I'll get less than 4, maybe I'll get 1, 2, or 3, maybe I'll get 4, or maybe I'll get a number bigger than 4, which are 5 or 6. So this is a casual event, getting less than 4. It may happen, but it may not happen. Okay, now the next thing, number 6 is classical probability. And I will define it like this. First, we denote the set of all possible elementary events to a given experiment of a given experiment, with now another Greek letter, omega. Okay, this is omega. For example, if I roll the 6-sided die, then omega will be 1, 2, 3, 4, 5, 6. Okay, if I draw a card out of the deck of cards, omega will be what? The ace of hearts. Then the next one will be the 2 of hearts, etc, etc, etc. And let's say the last card will be what? The king of diamonds. So all cards that are in the deck are part of omega, and there are 52 cards, so omega will have 52 elements. I have 52 possible outcomes out of the experiment drawing a card out of the deck. Okay, so B, if A is the set of favorable outcomes for a given event to occur, then the probability for that event to occur is P of A. P of A means the probability for the event to occur, for the event A, is Ni of A over Ni of omega. Okay, this is my formula for classical probability. So let's give an example. For example, the event is having a composite number as a result of rolling a die. Okay, composite numbers are those which have more than two factors, right? For example, 4 is a composite, it can be divided by 1, 4, or 2. 6 is a composite, it can be divided by 1, 2, 3, and 6. So when I'm rolling the die, I have two outcomes for getting a composite number, either 4 or 6. So A will be having the elements 4 and 6. So Ni of A, the number of elements in the set, will be 2. Omega, as I indicated before, omega will be the set 1, 2, etc, etc to 6. So Ni of omega will have 6 elements. So the probability for getting a composite number when I roll the die will be 2 out of 6. So this is 1/3. Okay. Another example. I have let's say a deck of cards. What is the probability to draw a king? Okay, I want to draw one card out of the deck and I want it to be a king. So the set A will contain the 4 kings, right? I'm not specifying which king I want. So I'll have the king of hearts, I'll have the king of diamonds, I'll have the king of spades. Now let me try to, okay, king of, imagine this is a spade, and then I have the king of clubs, right? Sorry, the king, this is the king of clubs, this is a club, and now I have the king of spades. So the spade was like a reversed heart, okay? So something like this, okay? Now you're seeing my drawing skills here. So Ni of A will have 4 elements in total, right? And now omega, Ni of omega, we have is going to have 52 elements. So the probability of drawing a king will be 4 out of 52, which will be 1/13. And that's the answer. Let's give another example. Let's say in a lottery, 2,000 tickets are printed, out of which 100 are winning a prize. Winning a prize. Okay. What is the probability? Probability to buy 1 ticket and to win a prize. So obviously omega will be any one of those, will contain the 2,000 tickets, because if I want to buy a ticket, I can buy any one out of those 2,000, right? And then if I want to win, the favorable outcomes of the event winning is to buy any one of the 100 that are winning, right? I don't care what I'm going to win, I just want to win something. So if I buy the first winning ticket or the 100th winning ticket, doesn't matter. So I have 100 outcomes of winning a prize, buying any one of those 100 winning tickets. So the probability of winning the prize will be just 100 out of the 2,000 tickets that I can buy. So this will be 1/20 or 5%. Okay, 5% chance of winning. If that is clear, the last thing just to mention, as you probably figured it out already, if A is certain, then the set A will be equal to the set omega, right? For example, when I roll a die, I want a number less than 10. The favorable outcomes for getting a less than 10 are all the numbers from 1 to 6. That's the same as all the possible outcomes. And therefore, the probability of A will be Ni of A over Ni of omega, which will be the same as ni of omega over ni of omega, which is the same as 1 or 100%. If A is impossible, then A will be the same as the empty set, okay? If I want a number that's bigger than 10 when I roll the die, I have no numbers that are bigger than 10, so I have no outcomes satisfying that event. The set of outcomes favorable to getting a number bigger than 10 when I roll the die is empty. It has no favorable outcomes, and therefore the ni of A is going to be ni of empty set, which is 0. There are no elements in the empty set, and therefore P of A will be 0 over ni of omega, and that is equal to 0 or 0%. And finally, if A is casual, A will be a subset of omega. Ni of A will be smaller than ni of omega, and therefore the probability of A occurring will be between 0 and 1. So it's going to be between 0 and 1. So between 0 and 100%, okay? Well, that's basically it. Thank you very much if you made it this far in the video. Next time we're going to solve some general problems from the topics that we've discussed so far, and I'll see you in the next one. If you like this content, like and subscribe. If you have any questions, let me know down in the comments below. Bye for now.